Hello, so this is our presentation on the action potential. And I'm sorry if I sound a little bit sick right now, it's because I'm still a bit sick, but that's okay. So the action potential is something that occurs within a neuron if that neuron is stimulated by a stimulus. And then if it is stimulated by a stimulus, it sends a nerve impulse down its axon, which can be received by another neuron that can also experience an action potential. So the first thing I'm talking about is the resting potential. So potential refers to voltage, so basically the resting voltage of our axon. So the resting voltage is negative 70 millivolts, and that just means that the inside of the axon is 70 millivolts more negative than the outside. And the inside and outside are separated by the axon membrane, which is like the cell membrane of the axon. So at rest, there are a lot of potassium ions inside and a lot of sodium ions outside. And there's also some chloride ions, but those aren't as important. And that's also why I heard someone call it like a salty banana, basically. So like the axon's like a salty banana because there's a lot of potassium on the inside and a lot of salt on the outside. So even though potassium and sodium are positive, the inside is negative because of negative proteins. And these ions do move around a lot because of leak channels. So potassium is going to move out because it has a high concentration inside, and then sodium is going to move in because it's like the opposite. And even though the ions are moving a lot, the resting potential stays constant because of the sodium potassium pump. So it basically maintains balance by using energy to actively transport 3 sodium ions out for every 2 potassium ions back into the axon. So that's what keeps the resting potential at negative 70 millivolts.
Next, we will be talking about depolarization. Depolarization is the upward curve of an action potential, and it occurs when the sodium channels open and introduce sodium ions to the inside of the cell. It changes the voltage from negative 70 millivolts to positive 35 millivolts inside the cell. A stimulus from a synaptic integration that causes the membrane potential to reach negative 55 millivolts or higher will result in an action potential. Depolarization is caused by the opening of sodium channels in the membrane and is an all or nothing phenomenon. As soon as the threshold is passed, an action potential cannot be prevented. The concentration of potassium and sodium ions inside and outside the cell can affect action potentials. A lower intracellular concentration of sodium ions can increase the peak of action potential. As the sodium channels mature, they start to fire off more rapid depolarization action potentials, and the subsequent increase in potassium channels leads to a shorter action potential reaction. The benefit of a faster action potential is that the neuron can fire more times in a period, and thus it can encode information more quickly. Saltatory conduction is the jumping of signals during an action potential between the nodes on the unmyelinated portions of the axon. These nodes, called the nodes of Ranvier, do not have a myelin sheath. The depolarizing current travels through the cytoplasm and the myelinated sheets of the axon. At each node, the membrane is depolarized above the threshold, causing another action potential in the next node. This node-to-node activation is called saltatory conduction. A benefit of this jumping of signals is the increase of conduction velocity over unmyelinated axons.
So repolarization is the downward curve of the action potential graph, and it's when the voltage goes from positive 30 millivolts down to negative 90 millivolts, and it's actually lower after repolarization compared to the resting potential because of hyperpolarization. So at the peak of our action potential, at 30 millivolts, the sodium voltage gated channels from depolarization are going to start to close, and then the potassium voltage gated channels are going to start to open now. So now instead of having sodium ions rushing in, we're going to have a lot of potassium ions rushing out of the axon. So that's going to bring the voltage back down to negative because we're losing a lot of positive ions. And hyperpolarization occurs at the end of repolarization because the potassium voltage gate channels take a while to close and they also open quite slowly. So near the end, we are releasing a bit extra potassium ions, which causes the potential to go more negative than resting. And that's what causes the refractory period. So we can't have another action potential until the sodium potassium pump can restore um, the resting potential voltage and the resting potential ion concentrations by pumping sodium ions out and bringing potassium ions back in.
So, the refractory period is the time it takes for a cell to return to its resting potential before another action potential can begin. During the refractory period, the cell takes a dive at its level of CML. There are two types of refractory period. The first is absolute, and the second is relative. Absolute refractory period occurs first and is a state when the neuron cannot trigger another action potential, no matter the simulation. The absolute refractory period only happens for 1 millisecond. The second type is relative refractory. The relative refractory period happens after absolute and is a state where the neuron could be fired again with a large enough stimulus. And this period lasts longer at 3 milliseconds. So after the refractory period is over, the cell should return to its resting potential and another action potential can be triggered.
A synapse is a connection between two neurons. So the neuron that's sending the impulse is the presynaptic neuron, and then the neuron that's receiving that signal is the postsynaptic neuron. So the terminal end of the presynaptic neuron, there's axon bulbs, and then those axon bulbs connect to the dendrites of the postsynaptic neuron, and they form a synaptic cleft. So there's like a little space between them, but they're not actually touching. And this is how neurons are gonna send each other information, pretty much. So the action potential, once it reaches the terminal axon, it causes depolarization there. And then now, instead of just sodium ions entering, there's now calcium ions that are going to enter the axoplasm, and then they're going to bind with contractile proteins that are going to pull vesicles that contain neurotransmitters towards the axon membrane at the synapse. So once those vesicles reach the membrane, they're going to bind with the membrane, they're going to combine with the membrane, and then they're going to cause exocytosis, and then those neurotransmitters are going to be released into the synaptic cleft, and then they're going to diffuse and then bind with some receptors that are on the membrane of the postsynaptic neuron. And those neurotransmitters, they can excite or inhibit the postsynaptic neuron. And since there's like so many of these uh, little reactions happening, the postsynaptic neuron has a lot of different signals from a lot of different other neurons. So its synaptic integration is like the sum or like the net of all that. So maybe there's like 3 neurons that are giving it excitatory neurotransmitters, and then maybe there's like 4 that are giving it inhibitory uh, neurotransmitters. So like the net would be inhibitory. So, but for example, if it's like excitatory, then if there's more neurons that are giving it excitatory neurotransmitters from synaptic clefts, then it's gonna fire an action potential potentially, maybe. So the excitatory causes Na plus to flow into the neuron, so that depolarizes the neuron, so it brings it closer to that threshold for an action potential. And the inhibitory causes potassium to exit or chloride ions to enter, which would polarize the neuron further and bring it further away from that threshold, so that it would have less chance to cause an action potential. And then after the neurotransmitters have been absorbed by the receptors, they are removed from the cleft so that they don't cause like continuous reactions or responses. So they're either broken down by enzymes or they're reabsorbed by the presynaptic membrane to be reused in vesicles. Agonists and antagonists are categories of drugs that can affect the synapse or their receptors on the postsynaptic membrane to influence the effect of the neurotransmitters. So agonists affect the synapse to increase the effectiveness of neurotransmitters, whereas antagonists are the opposite, so they decrease the effectiveness of the neurotransmitters. So agonists kind of mimic a neurotransmitter, and they can bind to the same receptors that the natural neurotransmitter can, and that just increases the response in the postsynaptic neuron. And some agonists can also block the reuptake of excess neurotransmitters, so that keeps more neurotransmitters in the synaptic cleft for longer, so that there's more for your body to use. So an example of a agonist drug is Xanax, which is anti-anxiety, and it kind of mimics the neurotransmitter GABA that decreases neuroactivity for a calming effect. And there's also Prozac, which is an antidepressant that delays the reuptake of serotonin, which is a neurotransmitter, so that there's more for your body to use. And antagonists, they block or decrease the effect of neurotransmitters, and some of them worked by preventing neurotransmitters from being released into the synapse. from the axon terminal, and others may bind to receptors to prevent those neurotransmitters from binding and creating response in the postsynaptic neuron. So some antagonist drugs could be schizophrenia medication, and they block those dopamine receptors in your brain. And alcohol can also act as an antagonist by blocking the release of glutamate, which is a natural depressant in your nervous system. And cocaine can also affect synapses. So when cocaine is introduced into the body, it heightens alertness and disrupts the circadian rhythm of your body. And cocaine works by inhibiting the intake of synaptic dopamine and serotonin. By binding to serotonin and dopamine transporters, cocaine it can also cause larger than natural amounts of neurotransmitters. So it's a psychoactive drug, meaning that it alters the availability of neurotransmitters to trigger action potentials. And they do it by either replicating the neurotransmitter in the body or by attaching themselves to the neurons.